In chapter 14, we are going to talk about some chemistry stuff. This is going to be start of kind of leaving physics and entering into the chemistry world. So the first thing we're going to learn about is about solids, liquids, and gases. In section 14.1, we're going to learn about what exactly is matter. We said that everything is made up of some kind of matter. So what makes up matter? And then we're also going to learn about the importance of thermal energy. So when you look at this picture, for example, we can see three of the different phases of matter. So we can see solid, which is the ice cubes. You can see liquid, which is the iced tea. And then you can see gas, which is surrounding everything really in this picture. And so these are going to be the main properties of matter that we're going to talk about. What are the differences and how they make up everything that pretty much surrounds us. So a couple of chapters ago, we learned about the difference between kinetic and potential. So kinetic has to do with movement, right? So we're going to learn about what kinetic theory means and how that relates to different, properties. So first of all, kinetic theory really pertains to how particles in gases behave. So when we talk about kinetic theory, we are going to also talk about when we say that gases behave, they behave in a way that relates to motion because gas molecules or the particles that make up gas are always in motion. So here are the four assumptions that have to deal with it. 1, all matter is composed of tiny particles, whether it's atoms, molecules, or ions. 2, these particles are in constant random motion. 3, the particles collide with each other and with the walls of any container in which they are held. And 4, the amount of energy that the particles lose from these collisions is negligible. So when we talk about the gas state, 1, we already said that the particles that make up the gas is always going to be moving. So if they're always constantly moving in random directions, that means they're always going to be colliding with each other. And they're going to be colliding with the sides of the container they're being contained in. When we talk about gas, there's no fixed volume of gas and there's no particular shape to gas that's measurable. And then also, they are going to fill whatever space they are in. When we talk about liquid state, we can apply kinetic theory to liquid and solids. So some of the assumptions we have or we talked about of, how, not mainly assumptions, but when we talk about the definition of kinetic theory, which is how particles move in gas, we can also say that particles move in liquid and solid state as well, and we'll see how that works. So in liquid state, like I said, you can apply the kinetic theory to it. In liquid state, particles that make up the liquid are also moving constantly, but they're not going to be moving as fast as they would in the gas state. They're going to have less kinetic energy because they're not moving as much as they would have in a gas state. So if you have kinetic energy in a gas state being the most, liquid state is going to be a little less than that. And then also particles in a liquid state, they can't overcome the attractive forces that hold them together. All molecules in the liquid state, they're going to have some kind of relationship with each other. So they're going to have some kind of bonding. And they're not going to have enough energy to break that bond or overcome that bond that they have with each other. So they're going to kind of slide past each other, which is going to give the feel of something being liquid or fluid. And you're going to be able to see that clinging model. And this is what this slide also just says what we talked about. They're not going to have, they will have a volume, unlike gas. Gas does not have a volume or a shape, but liquid will have a volume. And obviously it will, the shape, once you pour it out, is not going to have an actual shape, but it will fit whatever container that you put it into. And like we said, they kind of carry the relationship of sliding past each other because even though they're not solid, they do have some relationship with each other that they can't break. The solid state is when you have a definite volume and a shape. They are going to be closely packed together, as you can see in the picture. So there will be a relationship that one particle is going to have with the other particle that makes up the entire object. And even though they are going to be closely packed, they are still going to be in motion. But they're going to have very little kinetic energy because they are not moving a ton. And then particles in this state, they cannot overcome the attraction that they have each other, so they can't just break apart from each other and move while they're in motion. Now, a cool thing about solid state is that many solids have something called a crystalline structure, which basically means that they have a specific geometric arrangement that makes up that solid of whatever you are talking about. And a lot of times when we refer to this, we talk about ice. Ice has a specific crystalline arrangement that they have that does break apart when they melt. Let's talk about thermal energy. So in thermal energy, basically this is the total energy of materials that the particles have in the materials. So thermal energy is what basically causes particles in a solid to vibrate. Thermal energy is made up of kinetic energy, which is energy due to motion, and potential energy, which is when you have energy when an object is just simply sitting in place. Now, when you have thermal energy, this is when energy of individual particles and their motions and their forces between those particles are related to each other. And that is what thermal energy is. So when you were talking about thermal energy, you have to remember to talk about the energy of the actual particles and the energy that those particles have and their motion that they have, not the actual object that those particles make up. So I'm going to say it again. Thermal energy is when you're talking about the energy of each individual particle in an object and how they move and the forces that are between those individual particles. Thermal energy is not energy that the entire object contains or the interaction that the entire object has with its environment. Temperature is basically how hot or cold something is, right? How hot or cold an object is. Temperature is going to show you the average kinetic energy of the particles that make up a specific substance. If you talk about, 0 degrees Celsius, obviously those are going to have less kinetic energy than something at 100 degrees Celsius because one is going to be colder, therefore more solid. The other one is going to be more liquid. Okay, let's talk about changes of state. So if you have a solid plus thermal energy added to that solid, what's going to happen? So let's talk about iced water like you see in the picture. If you have particles in water and you add ice to it, what's happening? So the particles in the water are going to have a lot of random motion, less than a gas state, but more than a solid state. When those particles in the water are moving randomly and are moving quickly, and you add ice to it, which is a solid state, what's going to happen is the particles in the water are going to start colliding with the ice particles, or the particles that make up ice, and you are going to be actually transferring energy from the liquid to the ice particle, and the ice is going to start to melt. Okay, so really, you're not really having ice cool the water, you're actually having the water heat up the ice, therefore the ice starts to melt. Okay, so when you have this transfer energy that is occurring from water to the ice is going to melt because the surface of the ice particles start to vibrate. So when ice melts, the particles that make up the ice are going to gain enough kinetic energy from the particles in the water. And when they gain that energy, those particles in the ice are going to overcome the attractive forces that are keeping them together. And then they're going to start melting. So they're pretty much breaking that crystalline structure that makes up the ice, and they will melt. So what exactly is the melting point? Melting point is the temperature at which a solid becomes a liquid. So There are going to be two important definitions. One's going to be the melting point, which I said is the temperature at which a solid becomes a liquid. This is when when you basically break the arrangement that is holding the solid together. And so you're seeing how much energy is needed to have that occur. And then the next definition is going to be heat of fusion. Heat of fusion is the energy needed to change substance from solid to liquid at the melting point. Once the liquid particles hit the ice, which is the solid, the liquid particles are going to actually slow down because they're going to become more cooler. And therefore, you're going to have less kinetic energy occurring. So, again, when you go from a solid state to when you're going from a liquid to a solid, when you're going from a solid to a liquid, you are going to lose kinetic energy from the liquid because it's going to become more cooler. And then again, heat of fusion and melting point are two important definitions. Remember, melting point is the temperature at which solid becomes a liquid, and then heat of fusion is the energy needed for a change, to change a substance from solid to liquid at the melting point. So a couple other things to keep in mind is that when you have something freezing, it's the opposite of melting, right? Freezing, you're turning liquid to solid. Melting, you're turning solid to liquid. The temperature of the liquid is going to drop when you have it becoming cooler. And when that happens, you are also going to decrease the amount of kinetic energy. So the warmer the liquid is, the more kinetic energy you will have. When you also have something freezing, you are going to have more of the molecules become fixed because they're going to have a structure to it. And then freezing point is when you have a temperature at which a liquid turns into a solid. Let's talk about vaporization and condensation. So when you have a liquid go to gas, how does this happen? So when particles are moving fast enough to escape their attractive forces that are keeping them together, they are going to enter the gas phase, okay? So when this happens, overcoming the attractive forces so that it enters the gas phase, this is called vaporization. And there's two ways it happens, evaporation and boiling. Okay, condensation is pretty much the reverse of vaporization when you have a gas going to a liquid form. Okay, so condensation is gas going to liquid. When you have particles moving fast enough that they escape their attractive forces, which is what keeps them together, and they enter the gas phase, so now they're not having those attractive forces, this is vaporization. And there's two ways that vaporization can happen: evaporation and boiling. So in evaporation, one thing to remember is that evaporation is occurring at any temperature. Whether you are boiling something or whether you have a glass of water on your coffee table for multiple days, eventually you're going to notice that the water in that cup is going to slowly start to decrease because evaporation is occurring even at room temperature. And so what is the definition of evaporation? This is when you have enough kinetic energy to escape attractive forces of liquid. So you're having enough energy to break that attractive forces, and therefore the molecules are turning into water and evaporating. When you have boiling, this is the second way a liquid can vaporize. Basically, this occurs at a specific temperature. So evaporation can occur at any temperature, but boiling has to occur at a specific temperature. And this is based on the pressure at the surface of the liquid. So let's talk about the definition of boiling point. The definition of boiling point is the temperature at which the pressure of the vapor in the liquid is equal to the external pressure acting on the surface of the liquid. So liquid particles have external pressure pushing down on it, right? When these particles overcome this pressure, they will need energy to do this, to overcome this external pressure, and therefore you will have this boiling point occur. So I'm going to say it again because I kind of slowed down. But when you have a boiling point, like it says here, you're going to have the liquid particles that are being boiled. So say you're boiling a pot of water. The liquid particles that make up that water, they are having external pressure pushing down on it. And so when you have the particles overcome this pressure, which they need energy to do it, you will have that boiling point reach the point where that liquid will start to actually turn into a gas. Now, there's something called heat of vaporization. Heat of vaporization is the amount of energy that a liquid needs at its boiling point to become a gas, okay? So if we think about it, boiling point is when you have liquid, say in a pot you're boiling water, you have external pressure pushing down on that liquid. Particles will need energy to, combat or overcome that pressure. Heat of vaporization is the amount of energy that that specific liquid needs at its boiling point, which is specific, to become a gas, okay? So always remember, evaporation is not specific, boiling point is specific. Sublimation is when you have, it's the process of solid changing directly into a gas without forming a liquid. So at some pressures, some substances can go from solid to gas without going through a liquid phase. And that is called sublimation. And this is what happens with dry ice, right? Dry ice is frozen carbon dioxide. So it can literally go from a solid to a gas without having to enter the liquid phase. There's something called heating curves. Basically, this is a graph of a temperature on the y-axis versus time on the x-axis for heating 1 kilogram of water. It's going to show the temperature change over time as you keep adding thermal energy continuously to a substance. If you look at A and B, if you look at B, the line on the line graph, you can see that there's no change occurring at 0 Celsius because this is when it's at an ice stage. This is when the ice is melting, so there's going to be a constant line. When the line starts to go up at C, this is when the particles are in motion, and then at 100 degrees Celsius, this is when the water is boiling and the temperature is actually constant. So we talked about 3 familiar states. We talked about solid, liquid, and gas. Now, there's another state which is called plasma, and this goes beyond this state of gas. So what is plasma? This is when you have matter that has enough energy to overcome not just the attractive forces between its particles, but also the attractive forces within its atoms. And so when you have this, if you have a substance that's made out of atoms, what's going to happen is those atoms are going to collide with such a force that the electrons are actually going to be stripped off those atoms. Most of the matter in the universe is in a plasma state. Example, the sun, the stars, the universe. And so a lot of people don't talk about this, but this is something that we actually have occurring even as we speak. If you've ever walked on a sidewalk and you've seen that the concrete sidewalks have a seam in it, you probably might not even have thought to yourself, why is that? You might have just accepted it as the way that they created sidewalks and not cared. But the reason sidewalks, if you look in this picture, have a seam in it is because of thermal energy. On hot days, what happens is the particles that make up the concrete can actually separate and expand. So when you have an increase in temperature, increase in particle separation occurs, therefore the object expands, and this is due to thermal expansion. So when you have thermal expansion, you're going to increase in size of the substance when the temperature is increasing. So when we talk about thermal expansion, we can talk about thermometers as well, because when you increase in energy, particles in the liquid thermometer here are going to increase as well. So the liquid that's inside of this thermometer, once it gets hotter, the particles are going to start to spread apart, and when they start to spread apart, they will go up the little tube, and therefore you'll be able to tell what the temperature is. And, you know, a lot of times in thermometers, that's the best way to use liquid mercury or whatever it is, because they are able to expand at such a rate that you're able to not have to wait a long time to see the change in temperature, but it can be more immediate. When we talk about hot air balloons, this is the same thing due to thermal expansion. So how does it work? One, you have air in the balloon, it gets heated. And when the air in the balloon gets heated, the distance between the particles in the air are going to increase. So there's going to be less distance between the particles. And when you have less distance between the particles, you're going to have a decrease in the density of the hot air inside the balloon. And when you have a decrease in the density of hot air inside of the balloon, they are going to be more than the density of the cooler air on the outside of the balloon. Therefore, the hot air balloon is going to rise. Okay, so let's talk about water's strange behavior. So normally an object or any substance is going to contract, right? They're going to get closer together when the temperature decreases, except for water. Water actually expands as temperature decreases. So when you have a decrease in temperature, water particles actually move, even though they move closer. What happens is when they start to get cooler, water has positive and negative regions to it. So when the temperature drops, those positive and negative regions, they're going to line up with each other, and they're going to create pockets of empty spaces. And these pockets of empty spaces actually cause them to expand even while they're cooling, and therefore they also become less dense, and that is why we see ice floating in liquid water, because of that, all those empty spaces that compromise the solid structure of ice. Now, not all solids are going to melt at a specific temperature, okay? So they are going to, for example, butter. If you put butter out, they will melt over a range of temperatures. That's because things like butter, they lack crystalline structure and are called amorphous solids. This is also an example, can be glass, okay? So they lack a crystalline structure, and therefore they have different and unusual behaviors that are pertain to them. Another thing is called liquid crystals. When you have a liquid crystal, they don't lose their ordered arrangement when they go from a solid to a liquid, and they are responsive to temperature change and electric fields at various points. And you know, they can also, and we see liquid crystals in things like LCD screens on MP3 players, cell phones, TVs, and laptops, and that's what we call pixels. At what temperature is the pressure of the vapor in a liquid equal to the external pressure in that liquid? What do you guys think? So this would be true at the boiling point. What is the most common state of matter in the universe? Remember, universe would be plasma, because this is the state that the stars, the sun, all of that are in. What is the amount of energy needed to change a solid to a liquid at its melting point? This would be heat of fusion. Make sure to work on this assignment. It will be posted on classwork for the correct day it should be worked on. And I will see you guys in the next video.